Thanks very much, Ted. So the title of this talk is Quantum Eigenvalue Processing. Guanghao Lou is the other author of this work. Let me begin by giving you a little bit motivations for why we consider this problem. So it turns out that many quantum algorithms can be somehow reformulated as applying some linear algebraic operations on the input matrices. So a famous example is in this factoring problem or the Shor's algorithm. So there's a step where we need to implement the modular multiplication operation. And we can think of that, we need to do this eigenvalue estimation on that operation. And we can think of that as applying some threshold function on the eigenphases. The second example would be this problem of Hamiltonian simulation, where we want to exponentiate a matrix on a quantum computer. And that's, of course, a linear algebra operation. And we can also consider, for example, solving linear equations or doing this quantum search. And there are many other examples which I haven't listed here. But let's say if we have an efficient quantum algorithms for doing linear algebra, the hope will be that maybe we can work backwards so that we can use these quantum algorithms for linear algebra to solve some other problems. So with that in mind, I want to talk a little bit about the input model for matrices and operators. So in this work, we use this input model called block encoding. Hopefully you have already heard this terminology in some of the previous talks. But the idea here is that if you have a matrix or operator, after it's properly normalized, you can put that in a corner of a unitary, and you can access that by manipulating this unitary. So I want to say that this is a standard model that covers many other common input models, such as sparse operators or local operators. So this is also the input model that we'll be using in this talk. Okay, so here are two problems that maybe you want to consider solving on a quantum computer. So I put them side by side. On the left-hand side, I have this problem called quantum singular value transformation. So in that problem, you have a matrix. You have a singular value decomposition of that matrix. We have V sigma U dagger. So the problem here is that you don't want to touch the basis transformation. So you only look at the singular value part, and you apply some polynomial functions on that singular value part. So there was a quantum algorithm developed in 2018 for solving this QSVT problem. So it was found that that algorithm can be applied to solve some other quantum problems beyond the linear algebraic setting. Okay, so this is basically the QSVT story. On the right side, I have another problem related to eigenvalues. So here, I want to apply this polynomial transformation on the entire matrix. So if the matrix itself is diagonalizable, it's equivalent to applying the transformation on the eigenvalue part. If we have an efficient solution to this problem, it could potentially have applications to, let's say, non-Hermitian physics or transcorrelated quantum chemistry, or maybe more theoretical applications like solving linear differential equations or other problems. But as you might see, singular values and eigenvalues are two different things. So, well, first of all, the basis transformation matrices are not necessarily unitary, so they are generally invertible transformations. And secondly, the middle factor, the eigenvalues, are generally complex numbers, unlike singular values, which are real and non-negative. And finally, sometimes we don't even have an eigenvalue decomposition, right? So in general, we have something called Jordan form. And the key point here is that the middle factor doesn't have to be diagonal, the block diagonal in general. So because of these reasons, the previous QSVT algorithm is not suitable for solving this kind of eigenvalue problem. And the main contribution of this work is to provide a systematic solution to this kind of eigenvalue problems. And here's a quantum algorithm for eigenvalue transformation. We assume that we have an input matrix with a block encoding. I am assuming here that the input matrix only has real eigenvalues. So this assumption is not essential, it's not necessary. I'll tell you how to relax this assumption later. We have some desired polynomials, and we have a quantum algorithm that helps you apply this polynomial transformation on the input matrices. So again, I want to say that this algorithm can work for more general input matrices, but I won't have time to go into that general case. But for the simplified case where this matrix is diagonalizable, so we do have an eigenvalue decomposition. So in this case, the complexity of that algorithm is given by that expression there. So we have a dependence on the condition number of the basis transformation. So that condition number will disappear if you have a Hermitian input. And then we also have a logarithmic dependence on the degree of the polynomial. So that factor will disappear if you are running this algorithm on average case input. So in any case, the performance of this QEVT algorithm can nearly recover the performance of QSVT algorithm. So it's as efficient as you think it will be. We have a related quantum algorithm for solving the eigenvalue estimation problem, again, for more general input matrices. So the complexity of QEVE is given there. So it achieves linear scaling with inverse accuracy. So it's something known as Heisenberg limited scaling, and it's probably optimal for the problem of eigenvalue estimation. Okay, so now we have quantum algorithms for more abstract linear algebra problems. We apply this to two concrete applications. So the first application is to the solution of linear differential equations. In this case, you want to implement this e to the ta for evolution time t. The complexity of our new algorithm is given there. It achieves a strictly linear scaling with respect to the evolution time for average case input. We also apply these results to the problem of ground state preparation, which has been studied by many previous work on quantum algorithms, because people can hopefully learn the underlying properties of the quantum system using the solutions. So in this case, we develop a generalized version, a quantum algorithm for the generalized problem where the input matrices don't have to be Hermitian. It has real eigenvalues, so the ground state are still well defined. And in this case, the performance of the algorithm nearly matches the previous optimal results for Hermitian Hamiltonians, and it's probably optimal, nearly optimal. So this is basically the main results and also the main application that we had in mind. So in the following, I would like to slightly change the topic, maybe touch upon the technical aspect, hopefully give you a sense of what is going on behind this scene. Right, so remember in the eigenvalue transformation problem, we have polynomial, and we want to implement this polynomial on the input matrix. Let's say this polynomial can be expanded with respect to basis. So we have this coefficients beta j, and we have some polynomial basis pj. And we want to implement that on a quantum computer. So in the special case where this input matrix is a Hermitian matrix, and also the polynomials are Chebyshev polynomials, there's a very famous solution to this problem. It's given by the discrete time quantum walk. So you can just perform this quantum walk, and you can efficiently implement this. And after that, you can either take a linear combination or using some more advanced tricks like QSVT to achieve your desired polynomials. But the bad news is that this kind of construction actually doesn't work for more general input matrices or polynomials. So more generally, what you can do is you can only generate monomial bases like power functions, right? So you have identity a square, a cube, and so on and so forth. So you can only generate monomial bases, but that's in general not very good for implementing functions. So often cases we introduce exponential costs, exponential in the degree of the polynomial. So this is something that you need to avoid if you want to get an efficient quantum algorithm. So our approach to avoid this exponential cost issue is to use something called a matrix generating function. You see on the left hand side, so that is something that we want to implement. Here, L is the lower shift matrix. So its action is cycling through all the computational bases. So by applying that operator to as a zero state, you can generate all the polynomial bases you want. So that's our desired operator, but we don't know how to implement that directly. But by using this matrix generating function, we could get more succinct expression. So hopefully, we can efficiently implement that more succinct expression and thereby efficiently generating the polynomial basis. So this is indeed the case for Chebyshev polynomials. The matrix generating function is given by the expression there. It's a rational expression. So in the numerator, you have 2 terms. In the denominator, you have 3 terms. And I won't be able to tell you the details of how you implement that. But if you trust me, all of these operators can be efficiently implemented within block encoding. And you just invoke the quantum linear system solver to construct this rational expression. OK, so now that you have that matrix generating function, you can apply that to initial state. You get the desired polynomial transformation with some success probability. And that probability can be boosted up using some standard tricks like padding tricks or amplitude amplification. So yeah, but of course, you also need to generate the coefficients in this expansion. But if you want to generate a quantum state with n coefficients, typically you need a cost linear in the dimension. So you need a linear cost. But here we recognize that these coefficients are actually Fourier coefficients up to a change of variables. So we developed some techniques for you to prepare n Fourier coefficients with only polylog n gates. So it's a highly efficient subroutine, this eigenvalue processing. OK, so these are the like main technical aspect. Now I want to go back to the previous assumptions that I've made, and I'll tell you how to relax these assumptions. So I have assumed that all the eigenvalues are real. So that corresponds to the first picture, where all the eigenvalues are enclosed by this real interval between, let's say, between -1 and 1. So the corresponding polynomial, nearly best approximation polynomials are given by the Chebyshev polynomials. So the second picture should also be kind of familiar to you. So that's basically from calculus. You remember that when you have a Taylor series or power series, the region of convergence is given by a circle. So that corresponds to the second picture. But the question is, what do you say if you have a third picture where your eigenvalues are enclosed by a more general complex region? Right, so our suggestion would be you implement this thing called a Faber polynomials. So Faber polynomials provide a nearly optimal solution for polynomial approximations over a complex region. So the generating functions for the Faber polynomials are given there. Again, I don't think I have time to go into details, but this can also be efficiently implemented within block encoding. So by doing that, you can achieve efficient eigenvalue processing over the complex plane. OK, so another assumption that I've made is about the diagonalizability of the matrix. So I assume that the matrix is diagonalizable and have some condition number dependence. So in general, matrices can be Jordan forms. In this case, the performance of the algorithm will depend on the Jordan condition number. Or and also the size of the largest Jordan block. But sometimes these Jordan bases can be ill conditioned. So this kind of analysis may not be suitable for that case. But we have a second workaround where we consider this set called a numerical range. It's basically the expectation of the input matrices. But you need to be careful because this input matrix is no longer Hermitian. So this is no longer a real value as in like quantum physics. So this is generally a complex set. And the approach here is that you need to enclose this complex set in your Faber region, like some of these pictures, and you'll be fine to use this eigenvalue processing algorithm. Okay, so I guess maybe I can give a very brief summary. So in this work, we develop efficient quantum algorithms for processing eigenvalues of high-dimensional non-normal matrices. So we have quantum algorithms for eigenvalue transformation. So its performance nearly recovers the performance of QSVT for Hermitian inputs. We have a quantum algorithm for eigenvalue estimation. It achieves a Heisenberg limited scaling. It's probably optimal for this problem. We have a quantum algorithm for solving linear differential equations. It achieves a strictly linear time scaling for average case input. We have a quantum algorithm for this more general problem of quantum ground state preparation. It recovers the previous nearly optimal result for Hermitian Hamiltonians. And underlying all these improvements or new results is this algorithm for generating the Chebyshev or Faber history states. And it in turn depends on using the generating function, matrix version of the generating function. And we also develop some independent techniques for creating Fourier coefficients, creating n-Fourier coefficients with only polylog n gates, which might be of interest. And for open questions, so one question would be, all of these algorithms are developed for these more general linear algebra problems. And it could be the case that when you are given a specific problem, like maybe solving linear differential equations, you could get even more efficient algorithms. So it could be that some of these aspects can be touched upon in the next talk. And finally, here's a link to the paper and a link to some of the resources and Microsoft Quantum. And thanks for listening.
Questions, go ahead. Yeah.
A very nice talk. So two questions. The first is there's a dependence on kappa s. Is that optimal? So especially, can you envision some lower bound? Or for any of this? Kappa s.
Right, so the general expression that we have doesn't depend on kappa. So it depends on some matrix functions. That matrix function can be further upper bounded, so kappa will disappear in this further upper bounds. Mm-hmm. We currently don't know how to prove lower bounds for the kappa parameter, but yeah.
So thanks. The second question is that since the encoding of the history state uses the quantum linear system solver as a subroutine,
yep.
Then how does it compare with contour integral based methods when it is applicable?
I don't know very many applications of the contour integral approach. The only application that I know that lead to new quantum algorithm is, I believe, a paper by you.
There are a few others. Yeah.
Okay.
Thank you, but there are a few others.
So well, the quantum algorithm that I'm familiar with is to the application of solving linear differential equations.
Yeah.
So in that case, they are choosing the circular contour.
Yeah, right.
But you can't go very far to the right half of the complex plane because the function value is very large there. So I would just assume that the trick is you first divide the evolution into several steps, and you only apply this contour technique within each step. and then you somehow concatenate these steps. So in comparison, what we achieve here is, in some sense, we don't use the segmentation idea. So we apply this kind of thing to the entire evolution, if that makes sense.
Okay, so this history state avoids this notorious problem of exponential blowing up of the normalization factor.
In some sense, yes.
Okay.
So I think if you have a circular contour, the region is corresponding to the Taylor series. So in some sense, you are not using the optimal polynomial for that.
Very interesting. Thank you.
Yeah.
You mentioned later in your talk that one of the things you have to deal with is the fact that matrix might be non-diagonalizable. I've always thought that this is probably like not a big issue in algorithms. Like this doesn't actually come up because like almost all matrices are diagonalizable. Right? You can just add exponentially tiny error to all of the matrix elements, and like it'll just
That's
be
true.
So does it actually cause a problem, or like do you have to deal with this case separately, or can you just say that it's fine? Like we'll just do the analysis of diagonalizable matrices and everything will go through.
Right. So I agree that there is a mathematical result that says like diagonalizable matrices are dense in the space of matrices. But if you actually check the concrete, like if you do the error analysis for that argument, you see that that would introduce some overhead to the condition number. So you can find diagonalizable matrices that are very close to your target non-diagonalizable matrix, but you introduce a huge condition number, I think. So that condition number will scale with, I think, scale exponentially with the size of the largest size of the Jordan block. So if I remember correctly, the argument is that you have some Jordan form and you try to perturb the Jordan form so that you can get a diagonalizable matrix. But I would guess that that will introduce a big condition number if you apply that argument. But
Thanks.
Are there any further questions? If yes, go ahead.
Regarding the last question just now, what does your answer mean with respect to the robustness of this method? So if you like perturb the input matrix a tiny bit about the output?
Right. So as I showed here, there are two workarounds for the general non-diagonalizable matrix. The first one is depending on the condition number of the Jordan basis. That can be a problem if your Jordan basis is ill conditioned. But you could try the second approach where you look at the numerical range of this operator and you try to enclose a numerical range inside like one of these figures. And that will not have a dependence on the Jordan condition number. So you are good to go for that case.
Yes, we still have time.
Hello? Yeah. Okay, I understand that your method is a generalization of the quantum singular value transformation, right?
Generalization in the sense that is solving a eigenvalue problem.
Yeah, it considers a more general family of transformations. But at the same time, I see that the arguments you use in the derivation seems very different from the way the QSVT is derived. So I was wondering, do you recover the usual QSVT algorithm when you're in the case of a quantum singular value transformation?
Like, sorry, what's your last question?
No, I'm just surprised that it seems very related to the quantum singular value transformation.
Right.
But the arguments you use in the derivation seem very different. For example, the expansion is very different. So how are the two? Is there a connection between the two?
Right. So at a high level, if we ignore how these two algorithms works, the performance of this QEVT will nearly recover the performance of QSVT for Hermitian input. So if you run this QEVT algorithm for the Hermitian input, you can nearly recover the performance of the QSVT. For technical aspects, I think the issue here is that for QSVT, you can efficiently create Chebyshev polynomials. So that's quantum walk. But for QSVT, you are like the entire procedure is basically implementing some Chebyshev expansion of the function. That's easier to implement for Hermitian inputs. But for non-Hermitian input, the issue is that you want to find an efficient implementation of these Chebyshev polynomials. So that's the main point.
Okay, thank you.
Yeah.
Okay, so we are at time. In 5 minutes, we'll have our next talk, but let's thank the speaker again.
Yeah, thanks.